Last video, we introduced the perturbation theory. And this was basically a technique we use to sort of attack or analyze situations where the Hamiltonians are not exactly solvable, right? So we have some system with a Hamiltonian that we can't solve analytically. However, we're able to write that in terms of an unperturbed Hamiltonian H naught and a perturbation Hamiltonian, where this Hamiltonian is some exactly solvable system, whether it's the hydrogen atom, the harmonic oscillator, some system we know the solution to, right? So we know that that Hamiltonian acting on some unperturbed eigenstates is equal to some unperturbed energy level times those eigenstates. We know the eigenvalues and eigenstates of that Hamiltonian, and then it is perturbed in some way by this other Hamiltonian here, right? And what we looked at, what we introduced last time, was essentially we can write, the goal is to figure out what the energy eigenstates and eigenvalues are for our full system, for our actual Hamiltonian. And we saw that we can write those energy eigenvalues as essentially an expansion of a zeroth order term and then some higher order corrections to that, right? And we can take that out to as many orders as we want, but essentially we have the zeroth order energy, which is just the unperturbed energy, and then a first order correction, a second order correction, and so on and so forth. And we saw that those energy eigenstates can be written in the same sort of way, where we have an unperturbed energy eigenstate and then some first order and second order corrections to that. And what we ended up doing here is we sort of took this whole idea and we developed perturbation theory, and we ended up with these equations for, this was the zeroth order um, equation, and then we had a first order equation that we started to look at in the last video, and this ended up being H naught minus En to the 0 acting on the first order correction to that energy eigenstate is equal to the first order correction to that energy eigenvalue minus that perturbation Hamiltonian acting on our 0th order states. And this was our what perturbation theory gave us for our first order equation. And what we did was we looked at this in matrix notation, and we solved for our first order energy corrections. And what we showed in the last video was that the first order energy corrections was essentially just the diagonal element of that perturbation Hamiltonian, right? So we have that in general was equal to the the diagonal matrix element of that Hamiltonian in the unperturbed bases. Or if we wrote that in the position representation, this was just the integral over those unperturbed energy eigenfunctions. That overlap integral would give us that matrix element and that first order correction. And again, we were able to figure these out. It turns out you can figure out these first order corrections without any knowledge of how the eigenstates actually change due to the perturbation. They depend only on the unperturbed eigenstates and that Hamiltonian. Today, what we're going to do, we're going to continue to look at this equation and and figure out what those first order corrections are to our eigenstates. We're going to use this degenerate perturbation theory to find the first order corrections to that. And we're going to go back to the matrix equation, this form of the matrix equation. Sorry, our first order perturbation equation in matrix form. So let's go back and look at that. So last time, in the last video, we just, to go through this, we looked at the n equals 3 state. So we're writing this equation for the n equals 3 states in matrix form. And we went through and we looked at how the left-hand side of this equation can be written as, it ended up being just this E1 zeroth order to that times E3 zeroth order times C3 1 first order. It was a column made vector that looked like this. C3 2, where that third column was 0 because it ended up being, the third unperturbed energy state minus itself, and the rest of the terms were just this. Looked like this, dot, 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 all the way down. And that was the left-hand side of that first order perturbation. And the right-hand side over here ended up being, because this, unperturbed eigenvector is just a unit vector in that basis, we had essentially just taken the third column of this matrix, and that's our column vector, and it ended up being negative of the perturbation, the matrix elements of the perturbation matrix there, except for the third column had E3, first order correction to the third energy term, minus the diagonal element of that perturbation matrix, and so on. And in the last video, we go through in a bit of detail how we got here. But what we did in the last video is we looked at that n equals 3, that third row in this matrix equation, and that's how we solved this. That's how we got our unperturbed energy eigenvalue, or sorry, our first order correction to the energy eigenvalue. What we're going to do today to find the eigenstates is we're going to look at all the other rows. And that's what we're going to use to figure out what the corrections to the eigen states are. Basically, what we're doing is we're going to end up solving for these C3 terms. If you recall, these C terms, that was, for our first order correction to the n equals 3 state, written is just a column vector where those are the elements of it, right? So we're going to use the rest of these equations to solve for those, and that gives us our first order corrections to our energy eigenstates. So what is that? Well, if we look at, just choose some arbitrary mth row, so for some m row here, what that row gives us as an equation is E, the mth energy eigenvalue, minus the E3 to the 0 times M3 first is equal to negative that matrix element of the M3 state. So this kind of gives us our the equations that we're going to solve for these CM3s, right? And if we solve for that CM3, we end up with that third coefficient in our expansion ends up being HM3 bracket over EM to the 0 minus E3 to the 0. Or if we get rid of that minus sign there just to kind of clean it up a bit, it looks like this. We have that matrix element, the unperturbed eigenenergy minus the distance. So basically, this denominator is the distance between the basis vector we're expanding in. This coefficient is some coefficient times that unperturbed basis vector. How far is that away from the unperturbed energy state we're looking at? And this is what that CM3 coefficient looks like. And this works for all, this is for all rows in this equation here, except for, so basically M not equal to n. And that gives us our coefficient. So we've got all the coefficients now, or at least an equation for every coefficient in our expansion that tells us what that perturbed state is, except for the m equals n state. That's going to come from normalization. See how that works? Let's just consider what normalization means. You know, our state, inner product with itself, should be equal to 1 for that state to be normalized, right? And we can write our eigenstate in terms of, you know, to first order, our first order unperturbed eigenstate plus this first order correction, right? And that first order correction can be written in terms of our unperturbed states with form of bases. So this is sum over all m to n of C3m, the first order coefficients, times that mth unperturbed eigenstate, right? If we factor out the m equals 3 term here, we end up with 1 plus C3, 3, 1 times, oops, not m, the third unperturbed eigenstate plus m not equal to 3, C3m1 on the rest of those unperturbed eigenstates, right? So all we've done here is we've written our energy eigenstate in terms of our unperturbed and first order correction. We've then written that first order correction as a linear expansion or a linear combination of our unperturbed states, and then taken that n equals 3 state out of that sum, right? So nothing really too complicated there, but that means if we take this inner product, well, what do we get, right? We have 3 to the 0, oops, 1 plus C3, 3, 1, the complex conjugate of that, plus sum over m not equal to 3, C3, m complex conjugate of that, times those unperturbed bras. All of that inner product with this. Avoid you having to watch me rewrite that. When we take that inner product, so again, this is just that. When we take that inner product, because these states are orthogonal, all we end up with are the 1 plus C3, 3 complex conjugate times itself. So that's this term and this term multiplied together. All of these terms minus these terms, it just pulls out, you know, the ones with itself. So that is sum over m not equal to 3, C3m first order. Those coefficients squared. When we, you know, multiply out those bracketed terms here, we end up with 1 plus C3, 3, 1 C3, 3, 1 complex conjugate plus the magnitude of that squared. It's the sum over all of these magnitudes squared, right? Now, we have to keep in mind we're using an approximation. We're only taking things to first order. So we're going to drop all higher order terms, you know, sort of for consistency. So this is going to be equal to 1 plus C3, 3, 1 and its complex conjugate. Now, because remember, these are just coefficients, this is supposed to be equal to 1. We can take out a global phase and set it to whatever. So we have the freedom to choose this C331 as being a real number. We can take out some arbitrary global phase. So if we make that real, then that gives us that it has to be equal to 0. And that term for the coefficient of the unperturbed state, it ends up being 0, right? Which, coming back here, we now have we know the coefficients for every term that is. So again, we're looking at n equals 3 state, the n equals 3 state. We're looking for the coefficients, essentially, for the how to write that in terms of our unperturbed states. We have this equation we've sort of sorted out for all the states other than the n equals 3 state. And we've just shown that for the n equals 3 state, it's 0, right? So our n equals 3 state can just be written as m equals 0 to n c 3m times m, right, as a linear expansion of our unperturbed states. And we know that the those coefficients are equal to the elements of the perturbation matrix over sort of the distance of those energy levels from the unperturbed energy level. And that's for the m not equal to 3, and we know 3, that 3 state is equal to 0. So we have all the terms in this expansion. We have our first order correction, sorry, there should be a 1 there, to our energy eigenstate. We can think about this sort of geometrically in our Hilbert space, right? Why, this C33 term means is implying that the corrections to our state are perpendicular to the unperturbed state, right? You can sort of visualize this. Say I have some state vector, an unperturbed state vector in pointing some direction in my Hilbert space, right? Then I apply some small perturbation to my Hamiltonian that changes it, and it is no longer an eigenstate. We have to correct for that. To first order, that's just going to be a small rotation. It's gonna pull it across by some, correction to that, and that's going to be, the resulting corrected vector is going to be the same length. They're normalized, so all I'm really doing is providing some sort of rotation there. And what does this mean in our Hilbert space? Well, the only components of this correction are all going to be perpendicular to the unperturbed state, which is essentially what this is saying. All the terms for the vectors in this Hilbert space that aren't in that unperturbed direction can be non-zero, while the state or the terms in that expansion that are parallel to this perturbed state are going to be 0. So we have that. We've gone through this for the n equals 3 state, like we did last time and all that, but we can think about this in general. In general, we have sort of, this, sorry, way too far, this equation for our coefficients to the first order in the first order correction. So writing that in general, if we want to look at for an arbitrary nth state that we're finding the correction for, those m sort of components are going to be h m n prime over e and the 0th order correction to the nth energy state, 0. Or to write this in Brockett notation, right? These are the coefficients. If we recall, we're looking for some nth energy eigenstate, which we can write in terms of an unperturbed eigenstate plus this first order correction. And this first order correction again, right, can be written as a linear expansion in terms of those unperturbed eigenstates. And so we can write this first order expansion this first order correction, n1 of n, as simply the sum over m not equal to n of those matrix elements of the perturbation Hamiltonian divided by the difference in the unperturbed energy levels, all times those unperturbed energy eigenstates, right? So this is how we determine the first order correction to our energy eigenstates using perturbation theory. So summarizing all of this, our first order perturbation, what do we have? We started with, our first order equation, perturbation equation, that was this, and we used this whole thing to solve for all our different elements. We had our first order energy correction. Well, we let's go through this whole thing in just Dirac notation, right? If we look at the nth row of this equation, right? So we look at n, just take that and operate on this equation. We end up with this prime 0. And looking at this term, what does this give us? We have n0, h0, and first order correction, minus n0, e, n0, first order correction. It's equal to n0, e, n1, 0, minus n0, h prime, 0, right? Looking over here on the left-hand side, what do we have? Well, the easiest way to see this is this Hamiltonian can operate on this ket, or it can operate on this bra. And if it operates on that bra, we end up just having n0. It's an eigenvalue equation, right? For that nth state, the zeroth thing. And 1 minus, well, it's the same term there. So this ends up just being, these two terms cancel and equals 0. So we have 0 on the left-hand side. On the right-hand side, we have these two terms. So what does that give us, right? This just means that this term is equal to that term, or this can come out and we end up with En. The first order correction to that energy eigen state is just simply the matrix element of that perturbation Hamiltonian. So this is what gave us our first order energy correction in first order perturbation theory. And then again, if we look at the other rows of that equation, so again, just to rewrite, well, let's just take this and bring it down here. If we look at the other elements of that equation, and operate with m on that equation and see what we get there, we'll be able to figure out our first order corrections to the state. So if we look at that, again, this Hamiltonian operating on that is going to give us E m to the 0 minus E n to the 0 m 0 n to the first order correction to that state. Over here on this side, because we're looking at the m not equal to n states, this En is essentially, we have a Dirac delta function between these two, so that gets to 0. So we just have negative m0 h prime n0 there. This term here is just our CMNs, those coefficients. That's the projection of our corrected state onto that basis vector. So solving for that, we get CMN1 equal to negative m0 h prime n0 all divided by E m0 minus E n0, or taking care of that negative sign. Again, we just have CMN1 is equal to m0 h prime n0 all divided by E n0. The difference between those unperturbed unperturbed energy states. So our perturbed, our energy eigenfunction is that unperturbed energy eigenfunction plus this correction, which is summing over the m's not equal to n's of those matrix elements prime and 0th states over those differences, all times those unperturbed energy eigenstates. And that gives us our corrected or our perturbed energy eigenfunctions. And that's the non-degenerate first order perturbation theory. Interesting to note that the first order corrections to the energy involve the 0th order energy eigenstates. That sort of continues. The second order corrections, which we'll see in our next video, we're going to go through the second order perturbation theory, will depend on these first order the first order corrections to our energy eigenstate and so on. But for now, we've finished through our first order perturbation theory. Hopefully you followed that. Again, we'll discuss this a lot more in class. We'll even do some examples in our synchronous sessions and on the homework. If you have questions, reach out to me. I'll get back to you as soon as I can, and we can discuss them in our synchronous sessions. I will see you then.